In the lecture, we will learn reinforced concrete columns design. The preliminary calculation of reinforced concrete column design will be performed in this lecture. The column size can remain same for 5 stories as we will be using a 20-story structure which we utilized in the previous videos. The FC prime or compressive strength of concrete is given as 4 KSI or 28 megapascals, and the yield strength of steel is 60 KSI or 420 megapascals. The first dead load is of 8 inches thick slab or 200 millimeter thick slab. The second dead load is 15-inch deep drop panel having a size of 8 feet by 8 feet and thickness of 375 millimeters. The third dead load is consisting of 40 PSF finishes load or 1.915 kN per meter square. The live load consists of 50 PSF or 2.394 kN per meter square. We have to analyze and check the design. Design the reinforcement only for bottom story or story 1 columns. If the design is okay, the reinforcement percentage is less than the code minimum. For ACI it is 8%. And the design is okay when the column chest passes the PMM interaction stress check. Let's start with calculation of preliminary sizes of the columns which we will be using in ETABS. Let's consider the typical interior column. The column catchment area is 24 feet by 24 feet. The drop dead load on the column is 15 inch divided by 12 into 150, that is unit weight of this concrete, into 8 feet by 8 feet. Similarly, the self weight on the column is 51,200 pounds and the finishes load on the column is 23,040 pounds. The total dead load for single story on the column in typical interior column comes out to be 86,240 pounds. The total live load on the columns is 28,800 pounds. Adding up the ultimate gravitational combination using ACI code, we have 1.4 times of dead load, that is 1.4 into 86,240, and 1.2 times dead plus 1.6 times of live gives a load of 149,568 pounds, and this is the governing combination as the combination gives a higher value than the other combination. In this example structure we have 20 stories and the maximum gravitational load will be on the bottom column. So the maximum ultimate gravitational load on the bottom column is 20 multiplied by the ultimate load divided by 1000 to convert it into kips. The value comes out to be 2991.36 kips or 13,306 kilonewtons. The column cross section can be calculated by using the ultimate load divided by 30 to 40% of the FC prime. It is a rough number. I am taking the average as 35% of the FC prime. The ultimate load divided by 35% of the material strength gives us the column cross sectional area of 2136.68 inches square. Let's assume the columns to be taken as square columns in which the width of the column and the height of the column is same, and taking under root of the cross section area will give us the dimension approximately, that comes out to be 46.24 inches. I'll be rounding up the dimension to nearest even number, that is 48 inches by 48 inches column for story 1, 2, 3, 4 and 5, as the instruction included that we have to keep the column size constant for 5 stories. Let's proceed with ETABS and assign the column sizes of 48 inches by 48 inches to the columns in story 1 to 5. I have assigned the columns from story 1 to story 5, the size which we computed initially as 48 inches by 48 inches. Now let's calculate the preliminary column size for the rest of the stories. For the same typical interior column, there are 15 stories above the column in the story 6. The maximum gravitational load on the story 6 column is ultimate gravitational load on the story 6 column is 15 times 149568. This is the ultimate gravitational load which we calculated per story. Gives the load of 2243 kips on the column or 9979.2 kilonewtons. The column cross-sectional area is equals to ultimate load divided by 30 to 40% of the FC prime. Gives us the cross-sectional area of 1602.51. Assuming square columns, we have in a similar manner dimension coming out to be 40 inches. So we'll be using the column size of 40 inch by 40 inch for stories 6, 7, 8, 9 and 10. First we will set the visibility of the structure from story 6 to story 10. I am setting the visibility options as it will be easier to make the selection. Otherwise you will have to individually select the column and being careful that you do not select the column of other story. So we have assigned the column size of 40 inch by 40 inch on the stories 6 to 10. One important thing I have to explain here is that we used a stress reduction in the formula that can be seen with the red color as 30% to 40% of the material strength. The stress reduction of 30 to 40% is the engineer's size for preliminary size selection. Somebody may also use other assumption for initial size calculation, but in the end results after final analysis design should be same. The reason for strength reduction for 30 to 40% is due to the rough catchment area method does not incorporate the moments in the column as we only included the axial forces, and also due to negligence of shear force and wind and seismic load along with a P delta load amplification. In a similar manner, the preliminary sizes for other stories was to be calculated. So up till now we have calculated the preliminary sizes up to story 10. Let's proceed with above stories. So there are 10 stories above story 11 column. The maximum gravitational load will be on story 11 column is ultimate maximum gravitational load on story 11 is equals to 10 times of the ultimate load divided by 1000 to convert it into kips. And similarly we get the column's cross sectional area required and the dimension of the square column. So conservatively I'll be using round up to 36 inch by 36 inch column for story 11 to 15. Now let's proceed with ETABS on how to do it. So now we have assigned the column sizes of 36 inch by 36 inch on the stories 11 to 15. Now we have last 5 stories remaining. There are 5 stories above column 16. The maximum gravitational load on the story 16 column is calculated in the similar manner considering 5 stories. And we get the column cross sectional area and the dimension required. Try 24 inch by 24 inch for column from a story 16 to roof. Let's assign them in ETABS. I'll be setting grid visibility option to view all, as we have done assignments of the columns. And save the model. One important thing to be discussed as per the code provisions. The property modifiers for reinforced concrete structural element. Specific code recommends utilization of property modifiers to incorporate the cracking in structural cross sections. ACI code recommends the following property modifiers for the structural members. Our concern here is for the columns, so we will be using 0.7 of the gross moment of inertia in both dimensions. We will be selecting the conservative ones as the emphasis of the course is how to assign property modifiers in ETABS rather than going to code details. We can define the property modifiers from here as 0.7, but since we have already assigned the columns cross section and defined them, so we'll have to define the property modifiers in each cross section, which seems a pretty long task. So I'll be using a smarter method. I'll be selecting all the columns and click on assign frame property modifiers and assign the property modifiers from here. We needed property modifiers for moment of inertia. This assignment can also be checked if you right click on the column and see the property modifiers assignments from here. I repeat that the property modifiers can be assigned from the frame section properties, but since assuming that we have a lot of columns in the structure, so that wouldn't be desirable for going into each column's property and then modifying it as 0.7. Rather, we can override by selecting all the columns at once and assigning them property modifier as per the code. Since we have done assigning the column sizes, now we'll be proceeding with the structural design. These parameters we have already defined in the code design preferences, as well as the loads. Loads were already defined in the previous videos. So our analysis is complete. Now we'll be clicking on design. Start design check of structure. So we'll only turn on visibility of the columns. The first thing in the column design we check is the reinforcement percentage and the stress result. Apparently, it seems very difficult to check the reinforcement percentage as there are many columns. And according to ACI code, the reinforcement percentage should not exceed 8%. So we can also see here, ETABS usually follow the code requirements, and if the reinforcement percentage is exceeding 8%, it will fail the column. But 8% is already very high percentage, and you will have the reinforcement lapse in the column as well. So considering the lapped condition, I would always recommend you not to exceed 4% reinforcement limit, as it is a 20-story high building and it is definite that there will be lapse in the columns, the reinforcement lapse. And at lapse location, if we provide 8%, and then at lap location it would become 16% since the reinforcement is to be lapped. So I'll always recommend the maximum allowable percentage in a practical design to be half of the code's recommended percentage as maximum, since the building is high rise. So let's go to show tables and we'll restrict ourselves to 4%. You can see the rebar percentages from here and the column labels. Maximum reinforcement percentage we are getting is 2.14%. Let's say if you are getting here a value above than the maximum percentage that you have set for the design. So let's see if we have to find out where is this C20. So I'll click on undeformed shape and see. So we have turned on the labels so we can find out this C20 located at story 1. Since it is at story 1, so for clearer visibility, and still if you are unable to find it, you go to select, right click and show selected objects only. So here it are C20. We can verify from here that the percentage is exceeding. Display design info and rebar percentage. So we are getting a 2.14 percentage. That is okay. Let's say if you have to revise the columns per reinforcement, so you can increase the column size, and when you will redesign the column, its reinforcement will be revised. If you are increasing the column size, it is most probable that the reinforcement will reduce, but if it is working on the minimum reinforcement, then it will increase the overall amount of steel, keeping the percentage to minimum. So overall our percentages are less than the maximum, so we are doing okay. Since we are to design only the bottom story columns, so we will be going with story 1 only. The column's main bars are also called the vertical bars. The number of vertical bars are calculated as area of steel in inch square from ETABS divided by area of bar from this table. Let's see the area of steel from ETABS. For time being, I'll be selecting only the interior columns for design and the highest percentage conservatively. The highest percentage in the interior column I am getting is 2.14%. You can also turn on the visibility in terms of inch square. The units is set to inch and it is okay. So highest steel we are getting is 49.315 inch square. For story 1 to 5, we have selected column size as 48 inches by 48 inches. The vertical steel we are selecting is taken from ETABS as 49.315 inch square. Now we have to select a rebar. Let's say we are going with the diameter 10 bar, or it is also called number 3 bar. You can see here bar number 3 is having a cross sectional area. Bar number 10 is having a cross sectional area of 1.27 inch square. So approximately 38 bars. Usually we round up, but the number is very less significant, so we can keep the bars to 38. Now we'll be calculating the ties for the same column. The formula for calculating ties from ETABS is spacing and bar selection. We will be assuming number 3 ties. According to ACI code, if you are using number 10 bar as the main steel, then you can go with number 3 tie. But if you are using number 11 or above diameter bar, then you'll have to use for number 4 ties. So we are using number 10 bar for the main steel, so we can proceed with using number 3 bar as ties. The calculation of ties is based on number of legs. Since we have a square column, we'll simply be using 2 leg ties and into area of bar divided by AV from ETABS, and the unit to be set in inch square per inch. We'll click on show reinforcement for shear. And to verify the units are in inch square per inch, I'll go again here. So we are getting 0.04. Using the formula for ties, we have 2 legs of number 3 bar. The number 3 bar has a cross section area of 0.11 inch square divided by this number we are getting from ETABS as 5.5 inches. You can provide at 5 inches as well. So conservatively I am going with a smaller spacing. Number 3 ties at 5 inch center to center. The column sizes which we selected for the stories above this level are these sizes were based on preliminary. You can further minimize these sizes if they are too over designed, and all we are getting is 1% reinforcement. So for this video, the scope was limited to design of the bottom story columns, the bottom 5 stories. But we selected the bottom story column only as the highest steel was coming in bottom story from the bottom 5 stories. So we went with the most conservative reinforcement. The scope of the lecture was limited to bottom story columns from level 1 to level 5. So the story 1 to 5 is this level, and we selected the bottom story as we were getting the maximum steel in this story. So that is how we design the bottom 5 story level columns in a conservative manner. You can perform detailed analysis and simplify or reduce these column sizes if the reinforcement is coming too low or near to minimum. As the preliminary sizes is just to perform the analysis and start with the first iteration of design. Since the design is an iterative process, so you can keep on revising size. Let's have a look on how to check the columns PMM ratio or the stress ratio. So columns PMM ratio shows that the stress in the columns is between 90% to 99%. If the stress were more than or equal to 100%, then the column would have definitely failed. But here we are on the conservative side. Similarly, if you are dealing with high seismic zones, you can check the column beam capacity ratio, the strong column beam check. But those are specific code requirements. Specific detailing requirement for column based on code include the following and must be referred from the code, as the emphasis of the course is how to design using ETABS only. Maximum and minimum steel allowed, maximum and minimum transverse reinforcement allowed, seismic joint detailing and ties requirement, maximum and minimum spacing criteria for ties, maximum and minimum vertical bars spacing criteria.